We're just saying that if the time never ends, then the value would continue to increase infinitely. Next, our asymptote for this function, once again, is the horizontal axis, the x-axis, and the equation for that line is y equals 0. So again, we're approaching y equals 0, but we'll never actually get there. Even if this graph did continue and we were able to travel back in time, we would never actually get there. So y equals 0 is still the asymptote. The y-intercept is the value when t is 0, and that's right here in our table. It's also the a in the function that we plugged in. It's the initial amount that we sold this painting for, so that is the 1,800. So again, when t is 0, the value was 1,800, so that's our y-intercept. All right, we are going to run through example B and make sure that you can do this independently. So we have a real-world problem here. A baseball trading card is sold for $2, and its value increases by 8% each year after it's sold. Find the value of the baseball trading card in 10 years. These sound like really interesting problems where, like, that's real-life things that you could. This exponential function model works for if you're trying to calculate what your investment value will be in the future. So if you've got parents that do stocks or are investment bankers, this is the kind of stuff that they're doing. And this is how they can predict what the value of something will be in the future. So we have the baseball trading card is sold for $2. So what is that? That's our initial value. That's A. So we'll plug that in for A right here. Its value increases by 8% each year. That's the growth rate. And so we'll change it to a decimal. Be very careful changing your decimals. 8% is 0.08. So that is what will get added to the 1. We're going to go ahead and just combine and make that 1.08. Again, notice that we have in here our growth factor is a number larger than 1. That is why we're experiencing growth. Okay, because just like any number that you multiply, if you multiply any number by something greater than 1, you're going to get something bigger. So find the value in 10 years. 10 years is our time. So we'll plug in 2 times 1.08 to the t. I don't know why they make us continue to copy this over and over. And now we can plug this into our calculator. 2 times 1.08 to the power of 10 is equal to 4. And again, this is money. We're talking about value, so I would round to the nearest hundredth, which should be $4.32. Okay. Make sure you're using your calculator for these and not trying to raise something to the power of 10 by hand. That would take a long time. So after 10 years, the baseball trading card will be worth approximately $4.32. Not bad if you initially paid $2 for it. It's doubled in value. So, you know, if you're saving your baseball cards that you had when you were in elementary school and you're saving them for your grandkids, they'd be worth a whole lot more per card by that time. But just 10 years, like by the time you get out of high school or college, it's just going to probably double-ish in value, according to this problem. Next, we'll create a table of values to graph this function. So I'm going to go into my table. Oh, I've got to first put in the y equals. I'm going to put this value, this right here. This is what I'm going to put in y equals. Why will I put this one in? Well, we said that t time is the independent variable. So that's the x that I need to leave in my equation, in my function. So I'll put in here 2 times 1.08 to the power of x. Notice that's x or t. We can use there. Now I can go look at my table, and here I have what goes in my graph. Okay, so when time is 0, y is 2, so that's the 0.02. When time is 3, y is 2.5194, and that is the 2.5194. Okay. And then when y is 6, 3. So you see how it's kind of growing. When y is 9. So we're just looking into the future, basically. It's like a little crystal ball. And then scroll down to when x is 12. Y is 5, 0, 3, 6, 3. And again, you could scroll down farther. This is at 12 years. Oopsie. At 12 years, we're a little more than $5 for this card. And when we go to graph, I'm just going to quickly sketch because this interval is a little challenging. You can actually find the points if you like, but we're just trying to show you this growth graph here. So the domain in this case is all numbers, all real numbers for t as long as it's greater than 0 because we can't go back in time. And then the range is all real numbers greater than the initial value of $2, greater than or equal to. The asymptote this time is y equals 0 again, because if we extended this graph the other direction, if it's constantly increasing in value as time goes on, then if we could go back in time, we would assume that the value previously was lower and lower and lower and lower. So it would still approach y equals 0. That's almost always going to be your asymptote. So when in doubt, just put y equals 0. Let's see, the y-intercept is the value of y when t is 0. So that's when it's sold. And that was $2. All right, so I want you to try, go ahead and go over to page 10. I'm sorry, page 621, and you're going to attempt question number 10. And I'm going to work it silently. You can watch my process and follow along, or you can work it on your own and not look at the screen again until you've got the answer. All right, so hopefully we got the same answers. This graph looks a little bit more subtle because we have a much slower growth rate. 2% growth rate is not very extreme. So slow growth. And that is where we're going to stop for today. That is exponential growth. So all we've done today is exponential growth. We're in lesson 13-2. And tomorrow you'll watch the videos and do the homework for exponential decay. So for now, we'll go ahead and assign homework problems. And all the homework problems for tonight will be the exponential growth problems. And that would be problems on page 625, number 1, 3, and 5. And I think that's all I'm going to have you do tonight. All right, so tomorrow, exponential decay. It'll go a little bit faster now that you've seen growth, and then you'll have a few more homework problems tomorrow. Have a great day.